All righty, I think we are live. Let's give this a go. So, thank you, Grigore Rosu, for coming to be our third guest on how things work. Before we get things started and before we introduce you, we'll just read a short disclaimer. So, this podcast is for informational purposes only. Nothing said should be interpreted as an offer to buy or sell securities, financial advice, legal advice, or as an opinion of the employers at which we work. Lastly, our guests and I may hold positions in the companies or project discussed. Most of these people are founders, so that should maybe assume that. And then, the quick background here, how things work if it's your first time. Many podcasts are geared towards a non-technical audience and focus on the impact, but usually steer away from nuanced technical conversation about how these low-level mechanisms work. This is that. So we are bringing on great people that have deep experience in a lot of these nuanced topics to talk about what makes things go around in the world of blockchain. So with that, would love to introduce our guest here, Grigore. Tell me what's up. Where are you? What's your background? Where are you from? What are you doing these days?
All right. So thank you for inviting me, Patrick. And in what regards the technical depth, I'll follow your lead. So please stop me if I go too deep or tell me to go deeper. I'm Grigore Rosu. I'm originally from Romania, before you wonder where my accent is from. But I came to the United States in 96 for a PhD, like many of my colleagues, most of my colleagues from the University of Bucharest. And then after PhD, I worked as a research scientist at NASA Ames in California for 2 years. And then in 2002, I came to the University of Illinois, Urbana-Champaign, as a professor in my field, programming languages and formal methods and formal verification. And I've been there since then, where I'm actually right now. I'm in Urbana-Champaign right now.
Very nice. Yeah, the little known fact here is when we were first talking, found out, I shared, was my parents actually met at a Cubs game way back when. I grew up in Wisconsin, so very familiar with the area and heard great things. But yeah, it was really exciting to bring you on. I basically saw a demo you guys were doing at ETH Denver in your current work, and I thought it was one of the coolest demos I'd ever seen around, like, basically using this thing called K, which we'll get into, to make blockchain execution just a totally different thing than what most people are aware of or even familiar with. I think what's even possible today. And so given all the discussion around like RISC-V, WASM, LLVM, Rust, and everything that's going on into how blockchain execution environments are evolving, I figured this would be a great way to, I think, broaden the aperture for like what people actually think is possible to do on a blockchain and how that can really, really impact, I think, really the design elements here. So, I think to motivate things a bit, let's back up. So you started off, you mentioned as a research scientist out here at NASA at Ames Research Center. You were working on something at that time, runtime verification, semantic frameworks,
yes,
all of that stuff. What is that?
So in 2001, while at NASA with a colleague from NASA, Klaus Havelund, a very good friend, we were wondering what is between formal verification and testing, right? Testing helps you find bugs, but testing does not help you prove the absence of bugs, as Dijkstra said it very well. Now, on the other hand, formal verification helps you prove the absence of bugs, but it's very costly. So we're wondering, what can we have in between? Can we maybe do formal verification as we do testing? So let's run the program and do formal verification as we run the program. But of course, then we need the formal semantics of the programming language to understand exactly what's going on as we run the program. And that was the birth of runtime verification. We submitted papers to formal verification conferences, to testing conferences. Our papers were rejected in both because the testing conferences said this is formal verification. The formal verification conferences said this is testing. And then we came up with a new word, a new category, runtime verification. And it was very catchy in the community. We immediately created a conference. So it's an international conference called Runtime Verification.
Nice.
Then also I founded the company Runtime Verification in 2010. Here in Urbana-Champaign, and that was the precursor of everything. And now recently I founded Pi Squared, which is where we'll go very quickly deep into. So that's how we got here.
I think most people in the space are probably familiar with your work at Runtime Verification over the years, as you guys have partnered with a number of different projects on all sorts of formal verification and procedures for different smart contracts and
yes,
such.
Runtime Verification was the first security auditor in the blockchain space using formal verification. We formally verified Uniswap version 1 with Vitalik's recommendation. We also formally verified Casper, Vitalik's smart contract back then, and the deposit contract that everybody used to move their assets from Ethereum 1 to Ethereum 2, the proof of work to proof of stake. So we formally verified several prominent protocols around that verification. But we also saw lots of bugs and errors and bad designs of everything. And that's why we stepped back and said, maybe it's time to do things right. Now that we know all the things that can go wrong. And that's how we came up with Pi Squared.
So I think a lot of folks in the space, myself included, even like if, I'm not going to say before getting into this, but at least for, recent memory, you hear a lot about like, oh, we're formally verifying this thing, or this language allows you to do formal verification. And I think people just assume they hear that and they're like, oh, no bugs can exist. So like if something's formally verified, we're all good. So I think it would help actually to establish maybe like if you are actually trying to formally verify something, what are you actually doing? Because I think, a lot of people hear that like, great, it'd be awesome to formally verify this thing. And then
Exactly. That was a big problem for runtime verification because there were so many companies that claimed formal verification in the space, and users couldn't see the difference between actual formal verification and only saying the words formal verification. They just wanted a stamp of approval, and often they got involved with companies that didn't do formal verification at all, but they called it formal verification. So formal verification requires two things, right? So first, a mathematical model of the computational environment, programming language or virtual machine, whatever executes the program, right? You need to know exactly the rules of the game of the executing environment. Okay, so we call it a formal semantics of a programming language, but some people don't go directly to the formal semantics of the program, but you need somehow to say what the program does, computationally speaking. Not what, but how it executes. How it executes. We need to know how the program executes in order to reason about its executions. That's number one. And second is what the program does, some formal specification, some properties of the program, some expected properties of the program, the properties that you want to prove. Okay, and you can mess up very badly formal verification in both of these or in any of these two camps, right? So you can have a bad formal semantics of the programming language, and we've seen many of those, right? Or a bad semantics of your program, a bad mathematical model of the program. Because, for example, an example that I see over and over again, you take a Solidity program, and then you do what? You rewrite it in some other completely different language. Let's say Daphne. Daphne is a language that underlies an amazing, actually, formal verification environment. But there is a big gap between the Solidity program and the Daphne program. Who proves them equivalent? Nobody. You just believe that whatever mental model you had for Solidity, you translate it correctly into Daphne. Second, you don't even run the Solidity program anyway. You compile it to EVM, and then you run the EVM. The compiler can have bugs. And now you just hope that whatever EVM bytecode is executed will be very similar, identical, with the Daphne program that you now formally verify. And then you formally verify using this amazing formal verification tool for Daphne. But you also have to know exactly what properties you look for. And also, you have to translate those properties from Solidity to Daphne. Let me tell you a property that holds for any program in any programming language. Can you guess it? What's the property?
Ideally, that it terminates. I think it's maybe one thing, or like that it stops.
Well, it may not even terminate. No, that's complicated.
In a practical consideration, you want it to stop. I know that it's impossible to prove.
It's impossible
with the halting problem.
It's a very hard property actually to prove.
Yeah,
but there is a property which is very easy to prove. It's instantaneous to prove for any program in any programming language. The property is the following: true.
Okay. You can see how foreign. I mean, I think your readers will probably have the same question. Is like,
I know.
It's tough to even analog to these.
But you can always prove this property true. True holds for everything because true is true. Truth, it's the ultimate truth that holds.
Sure.
And you can prove it for any program. And actually, we have seen such formal verification attempts in Web3 where the properties people proved were extremely simple. Like I have one path through the program. Sure. Or I don't, on this input, I execute and I don't do a division by 0, or I'm checking a buffer overflow. Some very simple properties that had even nothing to do with the business logic of the smart contract. And then they claimed we formally verified. The program, which is so ridiculous and so frustrating. We stopped runtime verification, complaining because people wouldn't see the difference anyway, which was, I think that is, a lack of education, not only in Web3, but also in other fields.
It reminds me a little bit of like some of these like property or like model checking things that are often used in the consensus world too, is like you can specify it in something like a TLA plus, or I think Quint is now like a new approach. And it's like, cool, we formally verified that this construction is sound, and then time to implement it. Well, if the construction is sound, we must be fine, right? And there's a pretty big gap, I think, between what people think of the world of what's actually run in production versus what's actually run in testing
in the model.
In some capacity.
In the model, and then what you actually prove, how you formalize the properties that you prove. You see properties that, sometimes the property itself, they don't say it's true directly, but if you look at it and if you analyze it, it's almost like true. It's maybe saying alpha implies alpha. Or maybe not directly alpha implies alpha, but they say alpha implies beta implies alpha, which is also true, because it's very hard to think logically, rigorously. So you hope that the language framework helps you here. And
so when you mentioned like some people like kind of take the language for granted, like as you're doing this rather than actually even specifying the language. Maybe could you talk a little bit about the complexity of like actually coming up with the formal specification for a language? Because I imagine people just do that not out of the sake of just skipping it, but because it's probably very hard. Yeah.
In fact, actually, that is one of the simplest parts. It is not difficult at all. Misnomer. It is not difficult at all. And I can show you an actual complete definition of a language just to see how easy it is to define a language when the time comes. But let me tell you first that it's easier. It's easier than even implementing an ad hoc interpreter for the language, right? If you have the right framework, that's very important. If you write the definition by hand on paper, a mathematical definition of the language, all the axioms that govern the language, then it's hard. But if you have the right framework that allows you to keep testing and keep running programs as you define the language, it feels and looks as if you implement an interpreter. In this meta language called, in our case, the K framework, but there are some other frameworks as well. And it's not difficult at all. Actually, let me show you a definition of the language of a programming language in this framework. Let me see where it is. Oops, this is the wrong one.
No worries.
Let me.
I'll hide it till you pull it up there. Yeah, this is for people listening on the audio. If you want to switch to the YouTube to kind of see an example of this, I think that there are a number of different resources online too.
Right. So let me share. Actually, this is how the K framework works at a high level. Now that we are here, let me also describe that, and then we need to switch to another window.
Sure.
But right. So a framework, unlike a tool for a particular programming language, a framework takes the programming language as input, right? So for example, Python is an input to the K framework. That means that there is a definition, a file called python.k, and that file, python.k, describes the syntax and the semantics of every single Python construct to such a degree of detail and abstraction at the same time that you can take Python programs and actually execute them with the mathematical model. But you need some tools to help you do that. And now that's what we have on the right side. We have different tools, like an interpreter, for example. And all these tools, they know nothing about any particular programming language. So there is a complete separation between the left languages and the right, the tools. And that allows you to get all the combinations, right? So I can get an interpreter for Python. I can get a program verifier for Rust. I can get a symbolic execution engine for C. All the combinations work. And the nice thing about it is that now you can plug and play your language. Language is not... I know that sounds a bit probably surprising.
Yeah, let's stop there and unpack it a little bit, because it's like, how do you even, like with K? So I think K you mentioned is a framework for how you can kind of write these definitions of languages. How do you even start coming up with something like that? Because you want it to naturally be comprehensive, right? Like the whole point of it, ideally, is that you can reduce, any language into this framework. I think a lot of people don't even understand like what the I guess like that translation, or like what sort of things you would want to even support from a translation perspective.
So
like, a lot of these people are programming like for loops, if statements, and I'm assuming it's a lot more generic than what that would let you believe. Yeah.
So how about this? Let me show you a concrete definition of a language, a very simple language first, and then I will tell you how you can get to designing such a framework. All right, so I'm going to share my screen. I will pick a tab. Oops. Can I share my...
It's always fun talking to professors on the podcast, because it's their forte is going through everything in such a clear way. So it's always a treat. Yeah, there we go. So I think
right,
perfect.
So here is awesome. Here's a complete definition, a complete formal semantics, or you can think of it as an implementation of a language in K, in the K framework. Right. So there are two columns, left and right. In total, 39 lines. In 39 lines of K, you are actually implementing, but it's more than implementing. It's defining the complete formal semantics of a language, which now can be used to execute programs, to formally verify programs, to do symbolic execution of programs, to do everything you want to do with this language, even prove properties about the language, not necessarily about programs. Right. So let me go very quickly through the definition. So to the left, we have the syntax. To the right, we have the semantics. The syntax uses this BNF notation, or context-free notation, where you have non-terminals. The capital letters are non-terminals, like here, syntax, exp, exp, these are expressions. And then we have different constructs for expressions separated by vertical bar. This is case. This is how you express cases in BNF notation. So you see an expression can be an integer, an identifier, expression plus expression. Terminals are in quotes, right? So if you use any parsing framework like Yak or Bison, you may have seen things very similar to this. And then statements, which can be assignments, if then else, while, blocks, and so on. And let's focus on one of them, one of the static constructs, if then else. You see, if takes an expression and two statements, the then and the else branches. So, and now this is the syntax, and the K framework generates a parser, by the way, using the most efficient technologies that we have out there. That now with just this left column, it will be able to parse any programs in this language, imp. We call it imp from imperative. It's a very simple imperative language. What is a bit beyond syntax in the left side of the screen are these attributes, gray in color, in bracket. Like, for example, strict of 1 for if then else. That means that this construct is strict in the first argument, meaning that we first evaluate the first argument and then we worry about the actual semantics of the construct. But that's already like semantics. It's saying, I have to evaluate the first argument. All right, and I don't touch the others, right? So if I don't say strict 2 or 3, it means that I don't touch the other arguments. I only say strict of 1. All right, so now we know that with all these attributes on the syntax, we know the evaluation strategies of all the syntactic constructs, which is almost like half the job. Now, to the right, we have now to worry about the actual values, about the state. But we don't call it state, we call it a configuration in programming language semantics. In a configuration, you hold all the different semantic components that you need during the execution of the program. It's like this detailed mathematical core dump, if you want,
nice parallel
of the program. So in this case,
it prevents you from running into core dumps in theory, right?
But in this case, this language is so simple, the core dump has only the program and the state, which is a map. And now, as you see, there are one or two rules. These are the axioms, the mathematical axioms defining this mathematical theory of IMP. Usually there is only one rule per construct. Sometimes there are two. We have two rules for if then else. So if then else is the most complex actually construct here. And you see the two cases. You have if 0, the second rule, and if I, and you see the side condition requires I different from 0. So if 0 or if different from 0. It's like in C. Different from 0 means true, 0 means false. And let's look at the second rule first. If 0 underscore S underscore is the then branch. It's an anonymous variable that matches that the then branch, and S is the else branch. And this rewrite, this arrow is a rewriting or a one step of execution to S, right? So this is the axiom that defines the meaning of if then else, right? And the other case is going to the then branch S and ignores the second one. When you don't need a particular semantic component, you just put an underscore. That's an anonymous variable. So that's how easy it is. Or look at the rule for while, the next one. For while B is the condition, S is the body, you just unfold it. It's in one step.
So I'll ask the dumb question, right? So like you see something like this, and you're like, it's 39 lines, but it's arguably a dense 39 lines of a lot of logic in some of these constructors. Maybe on the left-hand side of the language specification, it's a little bit more spread out. But some of the rules, I think, on the configuration, you got to really understand what's going on here. Is I guess when you're working through a specification like this, or what we call this formal semantics, do you try to compile, I'm assuming, like a list of what are considered valid and invalid programs, and then just basically see that this parser actually does what you'd expect it to do? Or how do you actually go about developing these things? Because I mean, the context here, right, is like, I think any programmer has always had this maybe dream at some point that they could maybe develop their own language. And you see all these DSLs and whatever as like an example of it. And I mean, at least you've shown here in 39 lines that ideally, if you had some desire to design a language, you could just get all this extra stuff that usually prohibits you from designing it from just right out of the box. So if there's a way to actually develop that in a coherent way, I think it'd be great to.
So let me first clarify this. That this is not difficult. So I teach programming languages. I've been teaching programming languages for 23 years by now. And students taking the programming language design class that I teach, CS 421 at UIUC, which is
here's your plug for UIUC,
undergrad students, right? So they can write such definitions after 2 or 3 lectures.
Wow.
At the beginning, yes, exactly, because it's not that difficult, really. And the key, because you asked, the key is to have tests, to have as many tests as possible. And tests here, it's a 2-dimensional thing. Tests here are programs. You want to have programs together with input for those programs, right? That you would like to run with the semantics. And you start with the syntax. Usually start with the syntax, just define the syntax and parse the programs. And what K will do when you execute these programs to give you the abstract syntax trees. That's the result of the computation, because there is no semantic rule saying what to do with that syntax, right? So it gets stuck on the syntax. So you see if it parsed correctly or not. It's all very incremental. Then you start adding rules, and not only incremental, but it's also, some students call it addictive, because once you start adding rules and once you see more and more tests passing, then you feel really good about it, and you feel adrenaline that you want to finish it. Now you are close, and then you finish it. So if you define the semantics of an existing language, let's say JavaScript, right? Then ideally you should look for benchmarks and test suites that were designed exactly to evaluate the various implementations of JavaScript, and then use exactly those. That's what we've done. We defined more than 30 languages so far, and published them in peer-reviewed conferences, proceedings. And in all cases, we had test suites. For C, for example, we had more than 10,000 actually tests, test programs in our test suite. And each time we touch the semantics, we rerun all these tests. So it's a very, very serious business to define a formal semantics of a programming language. And why is this important? You can actually stop now the sharing so we can see each other better.
Yep.
So why it is so important to have a formal semantics? Because the formal semantics allows you to derive now automatically for any program its mathematical model. How this program executes. If you don't have a formal semantics, what you have to do now instead is to define a model for the program itself. If you want to reason about programming, if you don't care about reasoning about programs, then you don't have to. But now if you have a formal semantics, you have a general approach to give meaning to any program.
And so, yeah, I mean, I think like the question naturally is like, okay, sounds like a really cool property. What were people doing, just to focus on K a little bit longer, like what were people doing before this existed, I guess? Because like, you mentioned this is under development now for, quite a bit of time. So like, I'm assuming in your earlier days, this was not a thing that existed. Yeah.
Actually, the idea of K also came when I was at NASA and I looked at the state of the art. So we had a very strong group there built by Mike Lowry. There were like 25 experts in formal methods, formal semantics, program analysis, static analysis. We had the creme a la creme in the world, literally. People from all over the world were in that team, the strongest. And papers, we had like 15% of the papers in all the major conferences were from our group. And I was very disappointed, in spite of all that, of all the methods that we used to do formal verification, even of mission critical software. And what we've done was literally to model by hand, manually, in the most ad hoc imaginable way, the programs that we wanted to formally verify. So we had programs of 10,000 lines of code that we had to formally verify. And what we did, we implemented a model of that program in a different language, a mathematically grounded language, like Daphne, for example. There was a precursor of Daphne, Boogie, back then, in Boogie. And then we just hope for the best. We hope that our manually, written model was faithful to the real thing. So, but having a semantics allows you to do that completely automatically.
Wow. Yeah, I guess when you say mission critical, at least in the worlds of NASA, you mean mission critical here. It's actually like a spaceship falling out of the sky.
Exactly. So we did that with software that flew in space. In one case, we even found a critical error, and they didn't change it. They didn't fix the code. Because the launch was too close and they had to go again through all the certification process. It was too bureaucratic. So we decided to simply not fix the error. That was a simpler approach. But let's not get into that. Please.
Yeah. We'll leave that where it sits here. Yeah. The ship, that sounds like it hopefully went off all right. I think I guess like at least the thing that sticks out to me so far in this conversation is when people think about the increasing power of computing, I think they think more about functionality. But if you want to maintain the same functionality, there's a lot more you can now do, I guess, with the program to give you much higher level of assurance around its correctness or its behavior.
Yes.
So I think an interesting transition point here is like, why don't more people do this? Like, is it, you mentioned a lot of this like automated conversion into all sorts of tools and things. What are people using this for today, I guess, in these sort of constructions? Yeah.
So first of all, let me touch a sensitive topic here, which funny, a professor who got the Turing Award actually in computer science at some point made a funny remark in a conference. He said that he knows a few people who used formal methods and formal verification in real world, in industry, and each time they've done it, they published a paper. Right? So that's saying something, right? That there is much it's much easier to publish work based on such mathematical complex models than to make them work in real life.
Sure.
I have my own version of it. Others have their version of it, but my version of it is that happens because tools like the K framework were missing massively. So, and because of that, you basically needed to have a PhD to do any formal verification or any formal analysis or formal semantics of a programming language. You had to use some complex proof assistant and encode by hand the program. And in the end, after spending a lot of time to do that, then the tool was also disappointingly slow. In model checking, you have the state explosion problem. In formal verification, deductive verification, you have the problem of coming up with lemmas to help the automation. It's a very manual and slow process. So that's why we put actually a lot of emphasis on the K framework, on performance. And it got to a point where some of the tools that I showed in the previous on the right of the picture,
the interpreter and
the interpreter, for example, got to a point where they outperform handwritten ad hoc interpreters for the same languages. That happened several times so far. Even for EVM now, we actually outperformed Get, which is the most.
So I mean, okay, we'll pause there for a second. That's a big statement. So I guess my question is like, how could you do this? Are there like tricks that are language agnostic that you can now employ? Or I think that'd be a great conversation to go into.
Let me build on your computer science experience here, right? And let me give you an analogy. Okay. So suppose that you want to write a program in assembly for a particular task, or let's say in C++.
Hopefully never, but yeah.
Hopefully never. But suppose that you or anybody else, for that matter, any good programmer, right? They will write the program either in C++, or even C, and then use GCC to compile it, versus writing it in assembly.
Sure.
Okay. In theory, you can write a program in assembly which will be a lot faster, or not a lot faster, but faster. In practice, very, very, very few people can do that, because you have to look at all the details of the hardware. You know what you have there, how many levels of cache, prefetching, speculation, lots of tricks that you need to play as a human, low-level tricks to make your one program fast. Right? While compilers now, they are configurable. They learned all the architectures. They know how to generate the best possible, fastest data structures, how to do prefetching, how to do everything, pipelining and everything. Same with the K framework. Initially, it was dead slow. Even 1 year ago, it was like 10x slower than Get on the EVM. But now it incorporates the state-of-the-art knowledge, data structures, and algorithms in how to do fast indexing. It all boils down to indexing in the end, which is the following problem, right? Suppose that you have a lot of cases. Right? Like you have the semantic rules, and you are in a certain situation where one of the cases will apply. How can you figure out as quickly as possible, as efficiently as possible, which of the cases applies, so you know which semantic rule to apply? And this is where we generate some decision tree-like, binary decision tree-like structures. They are called pattern match automata, actually, where we can do, it's basically a compilation of all the left-hand sides of the rules in the most efficient possible way, where you check a bit, and from that bit, now you already split the rules in two categories, two groups. It's either this or that. Okay, check another bit, now either that or do like binary search until you figure out the rule very quickly. And apply it. So it got to a point where it takes constant time almost to execute, no matter how many rules you have actually in your semantics.
Wow.
All those you can still in theory do all these optimizations by hand, but in practice, very few, first of all, know them, second, bother, right, to go that deep. And if you look at the code for Get, it's actually not optimized much, because their motivation was to have code that is auditable. People look at it and they say, okay, this is a good implementation. In our case, the code is even more auditable. I showed you the definition, 39
Sure.
lines. Look at it and say, of course, for each rule. And push a button and generate something which is much faster than actual interpreters. So I think that's what changed the rules of the game. The performance of these tools generated from formal semantics. So now this performance is not an issue anymore. A few years ago, that was the main issue. Colleagues, very famous programming language scientists, told me, Grigore, this is all beautiful, but it will never be fast enough to be real. I think we passed that resistance threshold. Now, semantics-based execution is fast enough. It's comparable to normal execution of programs. But the beauty of it is that under the hood, it actually builds a mathematical proof. It's all mathematically grounded, all verifiable.
I mean, I think from that perspective, you could think of almost like LLVM as a competitor to this, where Rust, right? It targets LLVM, and LLVM is actually the compiler that turns it into machine code. The thing is, LLVM obviously doesn't export any sort of mathematical.
You know something funny about LLVM? It was invented in the lab next to mine at the University of Champaign.
Sounds like you guys should have talked more back then.
my colleague Vikram Adve, LLVM took birth in his lab here at UIUC, and he had a similar vision, but lower level. The vision was that you need a compiler framework that everybody translates to, and now from there we know how to compile efficiently. So K is above LLVM. And by the way, Vikram is a good friend, and we have several joint students, and several of these joint students are now at Pi Squared. They are
very nice.
Very top engineers at Pi Squared, semanticists. We have this job, semanticist.
No, that's a nuanced role, yeah.
Right. And what we do, think about it this way: LLVM is here, K is here, and what we have the implementation of K in LLVM. We have a translation. All our interpreters generate LLVM the most optimal possible way, and we've done that with the LLVM group. We had joint runs and projects implement this in the most efficient possible way. And now, you see, what we eliminate from the picture is translations of programs to LLVM, to compilers to LLVM. Now they are not needed anymore because we have K here, and now programs are executed directly with the K semantics, and then you compile as efficiently as possible to LLVM as well. So you get both.
Very interesting.
So you get both LLVM and this pipeline of optimizations, and K and its pipeline of optimizations.
Wow. Okay. So definitely a lot of work has gone into this.
25 years of work, more than 100 man-year work.
Wow. Yeah, that's crazy. I mean, I think
it has I think more than 50,000 pull requests and more than 500,000 lines of code at this point. The K framework is the largest formal methods system out there.
I think when people think about, at least my context with this has always been if you want all this formal stuff, you have to write in OCaml or some of these other languages that force that all the way up to the developer. And basically the claim now is that with a framework like K running at this speed, that it actually can match native execution because you're converting to this mathematical definition of the world. And then from there, using LLVM to target, whatever architecture you're actually running on, that you can actually have the best of both worlds and that you can export this mathematical proof that what you're doing is correct, but then also still run the same exact code that you were running in the test.
Exactly. Yes. So you run the same code, you get the same result. It looks and feels same like any other interpreter. But under the hood, it constructs a mathematical proof, which means...
Let's go into that. Yeah, exactly.
Which means that you don't have to trust actually K. I cannot care less if it's K or ChatGPT in the end who produces the mathematical.
Careful. Yeah.
I'm careful. Yeah, but what I'm saying is that even if K has a bug, the mathematical proof will not pass the proof checker. There is something amazingly beautiful about mathematical proofs. Is that they are very easy, probably the easiest possible artifacts to check. Right? So if somebody gives you a mathematical proof which is detailed enough, going all the way down to the axioms and the rules of logical inference, now you can check that mathematical proof with a ridiculously small proof checker.
Huh.
If you're a student taking CS 421, my class, then you would have to implement such a proof checker in your favorite programming language.
Wow.
We have more than 30 or so far. And for example, the Rust implementation has 450-ish lines of code, less than 500 lines of code. That's it. So with 500 lines of code in Rust, you can check the integrity of any mathematical proof about any programming language. Okay, so now what that tells us is that we don't have to trust K, because we are obsessed with verifiability, right?
Sure.
And pi-squared and runtime verification and everywhere. Right? One verifiability that's not negotiable, right? So how do I verify? I don't know how to verify if an EVM program executed correctly. Simply, I don't know because it's such a chaos there. Even if I have a formal semantics of EVM, now I still wonder, how do I make sure that the execution is correct? Correct with respect to not even specifications, but that's simply the EVM language definition, right? If you execute a program, say factorial of 3. Factorial of 3, 1 times 2 times 3, 6, right? And it gives you the output 6. How can I make sure that that execution is correct according to the semantics? What if it gives me 7, right, as a result? How do I know that 6 is the correct answer according to the semantics of EVM? And I don't know how to do that with get, with reth, or with any other interpreter. However, with the K, even with K EVM, the K semantics of EVM, if it gives me 6, why should I trust it? Okay, because K has 500,000 lines of code. It's a complicated beast. It's the biggest formal method system. That if there is anything certain about such a system, no matter who writes it, is that it has bugs. Okay?
Yeah.
So
usually the bigger the trusted computing base, right? The less bugs.
Right. Yeah. Exactly. Yeah. But we want a very small trust base. The trust base must be only the programming language semantics. That's it. And the program that you have, you say that this is the program that I want to run, right? That's the only trust base. And now if I execute the program with K, what will happen? It will generate a mathematical proof under the hood. And it will prove that factorial of 3 equals 6 as a mathematical theorem with a very rigorous mathematical proof that justifies it. And now what I can do is to check that mathematical proof with the 500-line proof checker. And now I know that whoever generated the mathematical proof, actually I don't care who generated the mathematical proof. It could be, I don't know, somebody in North Korea. I don't care who generated that proof. If it checks and it ends with the theorem, factorial of 3 equals 6 at the end, that's it. It's a correct, I say thank you, it's a correct execution of the program. And that's what K is specialized to do and optimized to do, to generate such mathematical proofs very efficiently under the hood. And we check them with the proof checker. So we don't trust anything, verify everything.
Wow. Yeah, I think what is the term in computer science? It's turtles all the way down. So like you think your language is this, then it's this, then it's this, all the way down. But this is pretty close to the bedrock.
You have to trust something. You have to trust something, right? So we trust the programming language semantics, and we trust the proof checker, the mathematical proof checker, which means that we trust the mathematical logic.
I'm just curious. Have you I guess the length of the language description must say something about the language complexity, I guess, at some way too. So I'm curious if you guys have concluded anything interesting around that topic.
But that's a very nice academic actually project. We had even a grant to work on that project, and so there is a certain complexity to the semantics. So essentially, if you can define, like I showed you on the previous slide with 39 lines, you can define each language construct in 1 or 2 rules completely modularly without looking at other rules, then it means it's a good language. When you have to define sometimes you have to add 100 rules for one language construct, only because that language construct is so intricate, right? Like take the go-to statement in C. It's super complex. I didn't even know that you can jump from inside a loop in a function, into a recursive function. You have recursion and then iteration in the loop, and you can jump from there into the middle of another function, somewhere completely different. And you can do a long jump, so you can also get part of the context. That's a horrible statement. but that says something about the complexity. Yes. So if the semantics is compact, and if you have 1, 2, 3, maybe at most rules per language construct, then means it's a well thought language.
Don't tell Bjorn. Yeah.
Yes. But you see, I think what we are getting to here is that the programming language is not that important, not as important as it may seem, and that's our thesis at Pi Squared. We literally don't care what programming language is used to write smart contracts. All we care about is the programming language to have a formal semantics, because now we have a notion of correctness and truth, because without that you have nothing, literally, just hand waving. And then any claim about any said programming language should come with a mathematical proof if it's true. Otherwise, I have absolutely no reason to trust that claim. Or I can trust the issuer of the claim because I decided so, because I trust you, Patrick, because you're an honorable person, and whatever you say, I will believe you. Yes, but if I want to not have to trust you, I will need a mathematical proof of the claim. And then mathematical proof is actually checked with this ridiculously small proof checker. And now this is you didn't ask me, but I'm jumping into it, and I know that you'll ask me more about that. This is where the second the pi in our pi squared comes from. Now we can generate a zero-knowledge proof that the mathematical proof was correct, was checked, and it was correct. Because we implement those 500 lines of Rust as a zero-knowledge circuit now. And that not only that checks the proof, but also gives you a cryptographic certificate that acts as an attestation for the integrity of the mathematical proof.
Yeah, I was about to ask how you actually make that mathematical proof useful. So, like in the raw form, how big is this like raw mathematical?
It's as big as the execution of the program. Imagine that you have a very detailed log, and you log every single step in the execution of the program.
So it could be massive.
As big, linear in the size. Could be maybe you have 2 or 3 steps of mathematical proofs per actual execution steps. You may not want to see all those, like applications of modus ponens, or substitution rules. All those happen automatically. But so it's infeasible to even store these proofs. So unless you really, really want to keep such a proof for, I don't know, whatever reasons, usually what we do, we just check the proof, generate a zero-knowledge proof, and then discard the mathematical proof. Because the zero-knowledge proof, it's same like in ZK VMs. When you execute a Rust program with risk 0, you get a zero-knowledge proof at the end. But you don't have the execution of the program. You can generate it anytime by re-executing the program if you want to. But the zero-knowledge proof now stands for the correctness of the execution.
So before it was like, okay, you do this execution, you get this massive mathematical proof out. You can check that proof is correct, but if you wanted to, let's say, convince someone else, or some sort of consensus construction, maybe, or like some set of validators that it was correct, they would have to either re-execute the whole thing, get the same proof out and check it, or you would have to send them that mathematical proof. Or could you not have done that?
Exactly. Exactly. And I can try to compress that mathematical proof to gzip it, to do all kinds, but it's still big. Or you can send the ZK proof, which is like the ultimate compression of the mathematical proof. That's how we think of ZK proofs, as compressions of mathematical proofs.
So I think that the interesting point here, and I think maybe this is where, at least when we talked previously, you brought up a good point, is like, but I can already do this with Rust and a ZK VM. Why would I want,
Yes, you can.
What's better about kind of taking it into this mathematical definition and then using that as your basis for proving rather than this like high, and I'm curious how you think about that, because I think there's a lot of complexities being hidden.
There are 2 levels here. Let me go with the simplest level. Actually, those 500 lines of code that I mentioned as a proof checker, we actually compiled that with SP1 and risk 0. And that gives us a ZK proof already. So we use that. Moreover, now we bring all programming languages to risk 0 and SP1 through this, right? Because now you don't need a compiler to risk 5 anymore, because we have another way to get the executions in the actual programming language, source programming language, to your ZK VM. right? By giving a mathematical proof of the execution, and now the ZK VM just implements the proof checker and gives you a ZK proof. I would claim that it's even more correct than suppose that the original language was Rust, right? Then compiling Rust to RISC-V, it's more correct to execute Rust with the semantics and then check the mathematical proof. Because now I don't have to trust the compiler. The compiler is out of the trust base. Okay.
Is there a world where you could implement the prover more directly, so you didn't have to like have this prover in Rust and then compile that to RISC-V? And because that's still a pretty
exactly.
I mean, for practical purposes, still much smaller than whatever these programs might be. And like you could keep it locked, but
that's a very good question, Patrick. It's just that I do not have impressive results yet to tell you, except that we are working hard on it. So we're implementing now our own ZK circuit specialized for mathematics. And we have some empirical evidence that it will be 1,400 times faster than the best of the ZK VMs doing what we discussed previously, implementing the proof checker in the ZK VM. Because there is a lot of overhead that you have to pay. It's like a double level of interpretation.
This is my question. It's kind of like, it feels like you did all this great stuff and now you're like, never mind, we're going back to the Rust.
No. Yeah. And we believe that actually this is the future of verifiable computing, which is universal and correct by construction and fast. Correct by construction because you don't have to trust any compiler, you don't have to trust any implementation of any particular VM as a ZK circuit. These implementations of VMs are huge. Some of them, like for ZK EVM, are larger than 1 million lines of code. For RISC-V, they are around 100,000 lines of code. So 100,000 lines of code that you have to trust blindly.
Yeah.
Because you cannot formally verify that, or you can attempt to formally verify that, but you'll have to make lots of assumptions, and it's a very hard problem. Well, what we do, we say let's separate concerns. The correctness of the execution, I check it mathematically. I don't need to worry about that complexity at all in the circuit, in the ZK circuit. And now the ZK circuit only checks mathematical proofs. For mathematical proofs, you have only 12 proof rules. With 12 mathematical proof rules, you have first order logic and actually also second order and any other level, in logic. So you can have any mathematical proof about any theorem checked or can be constructed with only 12 mathematical proof rules. One of them is modus ponens. If you prove alpha implies beta, now you can conclude beta. So that's how easy the proof checker is. So yes, so we are working on this circuit and hope to have some results in a few months. And our hope is that it will compete with the actual handwritten ZK VMs for specific VMs or ISAs, the same way as the K interpreter now competes with handwritten interpreters for different languages. My firm belief, and I stick to this, and this will be, me.
Recording for the record here,
Yes, so for the record, I firmly believe that people should not implement any language-specific tools. All these tools should be generated by frameworks. You should define only the formal semantics of the tool. You should only say what the language is, not to implement it. We should use AI to implement languages. We should use soon, I'm confident that soon AI will generate better binaries than compilers, for programs. I take a program and say, hey, give me the fastest possible binary. ChatGPT, give me the fastest possible binary for this program. And it will run because the rules of the game are not that complicated. They are very mechanical, very, And why should we spend the time to implement these tools? Yeah, I don't know.
This was pre-LLM days, but I remember there was a class I took back at Stanford where there was a professor that would basically, export, a compiled version, I think it was of OpenSSL, and was like, he had some tool. It was a totally different approach to like actually optimizing this. And I wish I remembered the guy's name because you probably know him. But it was basically like a kind of an explorer where we'd randomly try to insert different transformations of like this machine readable code with different assembly using new instructions that maybe are not properly utilized maybe on x86 stuff. And there was like a non-trivial increase they found in the speed of OpenSSL by like changing the way some of these instructions were used and executed. And the idea that we're not at the frontier of what those compilers might be is not necessarily surprising to me, at least. But that's an interesting lemma that you can, if you have a tool that is what we'll call like the great unifier of all these random languages, you extract their commonality. In this case, the reduction to like a mathematical form, and then you just optimize how that mathematical form is interpreted instead. It seems like there's a lot of tricks you could just do once, and then all of a sudden everyone gets the benefit of that.
Exactly. For example, a very simple trick is to, whenever you have a basic block, okay, what you can do, you can mathematically summarize the semantics of the block, okay, into just one statement. Let's say block 22, the statement that has the meaning of that entire block. It will change these locations, it will do this arithmetic on the locations, and so on. Okay, so now in mathematics, and now when you execute programs, I don't go anymore through each instruction. I execute them all in a bulk because I already summarized their meaning once and for all, which is the same thing that you see in mathematics. Which is the same thing that you see in mathematics when you prove lemmas first. You prove lemmas, and then you use those lemmas to prove the theorems, right? And those lemmas make your proof of the theorem more compact, more easy to understand, right? So it's the same concept. You can do a lot
of intuition makes a lot of sense now to me.
You can do a lot of proof engineering, mathematical proof engineering, optimizations at the mathematical level, which you know that you cannot mess up because you still have to produce a verifiable proof in the end. You cannot cheat, but you can optimize the proof a lot. For example, we formally verified Uniswap. And Uniswap that has a function, square root. And the square root function is calculated with a while loop because you don't have square root, EVM in the library. So you have to. There is a while loop that calculates some divisions and multiplications until a fixed point is reached, and then it gets out, and that happens to be the square root, right? So what we did, we formally verified the square root, and we proved that it is square root once and for all. The lemma, right? The lemma says that this is the square root function. And now, whenever you call that function, say you call it square root of 100, we give you the answer 10, and the mathematical proof, which is much smaller than the execution of the program.
Yeah, sure.
And then you get a ZK proof of that, so you generate ZK proofs for the correct execution of the program faster than even running the program.
I get it now. Yeah, I think it only took me 57 minutes to really get an understanding of this. But I think, so I think the takeaway for me is like the compiler with its instructions can only conclude so much because it is not a mathematical proof of some reality, I guess we'll say, in the world.
Yes.
And if you instead reduce it so far such that it is, you can apply all sorts of different properties that the compiler would be completely unaware are even safe to do, basically, in the same model.
Exactly. The compiler will have to reverse engineer a lot to figure them out, and that's risky.
Wow. Is there a term for like that sort of like reduction or like step of like taking these mathematical proofs and or like kind of the code and simplifying it in this way? Like I was looking at some of the LLVMK papers and I saw this like compositional symbolic execution. Is that kind of related to this concept?
Yes, Patrick. Yes, exactly. That's the term.
I try to do a little homework with these podcasts.
Yes, compositional symbolic execution, CSE. That's what does the job for us. It extracts basically all the lemmas, if you want, all the basic blocks from the program, and it executes them once and for all symbolically, summarizes their behavior, and now each time you execute that block, you just instantiate that behavior that you already did once. It's very similar in spirit to type checking, but goes a lot further, right? In type checking, you type check statically a certain piece of code, and now you don't have to check the types dynamically anymore. You know that you are not going to multiply 3 with a string, right? So you don't have to check it at runtime. Same here, right? Once you summarize the effect of the block, now you know what the block does. You don't need to re-execute it each time. It's a bit like just-in-time compilation, but it's all in the end.
That's such a cool trick. Yeah, that's awesome. Yeah, I think wow, that's cool. Wow. So you said you've got 30 languages so far.
Yes.
That do this now. I think there's a lot of debate, and we'll go into actually how you guys are planning to use this and employ this in different ways. So I think that was the thing that first, like, if you're talking about motivating it, I was like, that seems crazy. But to back up, like, people think about blockchain execution environments as not this. Let's put it that way.
Yes.
And so when people are talking about, oh, we run WASM, or now, like, what Vitalik posted something a day or two ago about just doing RISC-V instead of the EVM because it makes it easier to prove. Why not K for something like this, or like kind of reducing it to something like where this goes? Because to me, this seems like it checks the boxes that they all care about, but I don't know if people just aren't familiar with it, or where the hang up is.
So I asked myself exactly the same question, starting with 2020-ish or so, when we saw the first really meaningful performance results of the K framework. I said, hey, this can actually be a lot more than just a framework for formal reasoning about programs. This can actually be an execution, a correct by construction execution environment for programs. And blockchains are in desperate need of such a correct by construction execution engine, because all this post-mortem security auditing and verification of programs would be avoidable if we had the right execution environment based on the actual semantics of the programming language. And that's when the idea of Pi Squared as a company took birth, with exactly this goal in mind. We want everything to be verifiable. So there are 3 words that were not negotiable when we started. Universality. It should work with all programming languages and all VMs, because it is simply ridiculous to go to to buy a computer and you say, hey, I want to buy a Python computer. You don't say that. Right? Or I want to buy a Rust computer. No, you buy a computer and then you can run all programming languages on it, right? It would be ridiculous to even think differently. So we talk about the word computer. The word computer should work with all programming languages, period. Okay? So universality, not negotiable, all programming languages together. Second, correctness by construction. Okay, it means that there is nothing to formally verify, nothing to prove. I don't need to prove anything, because computation is mathematical proof. We know that. That's what I've been taught myself by my professor, by my masters, that computation is proof. Computation is deduction, right? With the K framework, we finally made that literal. Now we can extract the mathematical proof from the computation, right? So if we go this way through mathematics, then we know that everything was correct. I don't have to go post-mortem and do verification of things that should not exist first place, right? So again, universality, correctness by construction. And 3, performance should also be good enough. And now we have evidence that actually if you go this way, sometimes when we do things right, performance not only comes, but you can get amazing performance that was not possible before. Like this mathematical proof engineering optimization, ESC and all this, that you cannot do those in a compiler, because the compiler now has to do symbolic execution, has to do formal reasoning. For that, it needs the semantics of the programming language. So it needs to reconstruct what we already have. So universality, correctness by construction, and performance. And the correctness by construction comes from verifiability. So you want to verify. You don't want to trust only that it is correct. You put it very well, that, hey, I can ship you the mathematical proof and then you can check it yourself with your proof checker. But shipping you the mathematical proof, that's very, very expensive.
Yep.
But you still want to verify it. If I verify it for you with my proof checker, then you say, why should I trust Grigore?
Yeah.
You can trust the proof checker, but why should I trust Grigore that he really ran that? You may give me maybe a TE, you may give me your proof checker in a TE, and then I can run it for you. That is an option. Why not? But the basic philosophy of pi squared and the thesis of pi squared was precisely what you said, that now we can build blockchains based on this new paradigm, which is now feasible and closer to reality than ever, namely that we can support all programming languages, plug and play your language, same like the K framework allows you to, then verify, don't trust, verify every execution using a proof checker. And now using different mechanisms, you can generate a proof of the proof check that happened. There could be a ZK, or it could be a trusted entity that signs, or anything else. But you see, separation of concerns is a golden principle here. I don't want to mix anymore, and I will never do that. I will never work with any student who even brings that up, right, anymore, which is to develop a tool for one language, one programming language, not even parsers. I mean, people don't really write parsers anymore, right, by hand for language. You use parsing frameworks. Should push the envelope. Let's go to semantic frameworks as well. And once you have the semantic framework, you can generate everything from that: interpreters, compilers, even ZK provers for that particular language, from just one definition of the language.
Wow, I think I'm sitting down. Yeah, no, I mean, it's a broad vision. I think it's a really cool way to think about the problem, and yeah, I mean, it's obviously built on decades of research into this problem space. So it's not something that it just came out of nowhere. Because I think that, I mean, if I was listening to this conversation, like not knowing you, not knowing my experience, there's like this sense of it feels too good to be true, right? Like you're kind of you're getting all these extra properties, and it's faster somehow. And so I'm not sure if you kind of have some explanation for that we haven't already covered, because like I think like earlier we kind of talked about there's reductions you can do here if you kind of represent the problem in a different way. And maybe the thing that people need to just think about is the way that you interact with programs and the way they're compiled is just one way to think about the world, and like one way to put together this abstraction for actually turning it into something people can run. But there's other ways, and this is just a very different way to think about that problem.
Yes. Yes, and indeed there is a lot of work behind this, not only on the K framework and my group and my researchers, but also before that, my advisors, other people who shaped the path, right, to get here. It was always the performance argument. Nobody argued that we cannot use computation to mathematical proof, that we can do rigorous analysis. People agreed, but then when it got down to numbers, they were always like, orders of magnitude slow down, sometimes 1,000,000 times slower to execute a formal semantics. And even now, if you execute a program with, let's say, lean, using a lean semantics, it might be 1,000,000 times slower than normally. So there was a lot of effort put into this. But yeah, I don't know what to say. But we encounter resistance because people don't understand it immediately, and people don't like things they don't understand.
The translation, I think, for a lot of people from like what looks like a program into what you are calling math, I think is a leap for a lot. I think like
but
the
it's
same
also under
concept
the
in
hood.
ZK.
It's also hidden. It's hidden. It's under the hood. You don't have to be aware of it. Actually, that's what we've done with the VLM blockchain that you looked at. You said you watched the video.
Our
demo in Denver. So what we did, we literally built a blockchain. Now that we know what K is, it's really K disguised as a blockchain. Okay, so you can plug and play a new language using a transaction, sign it with MetaMask, plug Rust, voila, now you have Rust. Now you want to write Rust programs, you can upload the smart contract in Rust and execute it. At the same time, you have WASM, you have EVM, you have Python even. and all they coexist because there is this common ground, which is mathematical proofs under the hood. Everybody goes through the mathematical proofs. And the fact that you make a call from a Python program into a Rust program may look like something super complicated if you think just compilers and implementations of them. But if you think mathematics, then it's just using a theorem in another theorem to prove it, right? So if you're an engineer and you want to prove the stability of your bridge, you may use Pythagoras theorem in your proof, right? Just use Pythagoras theorem. Doesn't matter the Pythagoras theorem was proved using trigonometry or some other means. You can now just use it because it's a truth, same like any other truth.
So I was going to ask, yes. I mean, like, when you're actually adapting this to like a blockchain environment, there's a few things that are not just in a pure program, right? Like something like state, like persistent state, something like interaction between these programs.
Yes.
How are you guys thinking about that problem? I guess because like eventually, I guess the puck has to stop somewhere.
You need to standardize. You need to standardize certain things. So what we decided to do in this quick prototype, which literally we built in a few months, 3 months or so, right? We built a whole blockchain basically from scratch that you can have multiple languages into it. So what we did, we used Ethereum. We used Ethereum's conventions, like the ABI encoding, the storage, and then we defined the language semantics of other programming languages on top of that. Right. So if you remember in the semantics, the 39-line semantics of E that I showed you, there was a map at some point, which was the state. Right. So now we have a way to hook things in the semantics to a library under the hood, and there we can say, hey, I want this map to be actually a key value store as in Ethereum. Okay, and then you define the semantics on top of that. But that's easy to change. If you want to change the architecture, you can change the semantics slightly, and you can adapt it.
So at least in that construction, like just to make sure I'm understanding. So like if you let's say in Rust had a map or some sort of interface like that, or let's say in Solidity, because we'll keep it basic, right? Basically, the user, like the one developing the program, would use like some sort of language capability, and then behind the scenes, it would map to actually like what the storage interface was in whatever like the underlying execution environment was, or is there some sort of SDK or something that you would need to use in each language that you wanted to interact with?
No. You don't have to use an SDK. You just have to know the conventions that different programs have for the storage. Right. For example, if
you can kind of overload existing language semantics because you're in control of the entire language, I guess, in that way, and with the full specification of that language.
Right. So so it's not really recommended to look into the state of another smart contract anyway. Right. Just use the API. Right. Use the function.
The public interface.
Getters and setters.
Sure.
Right. So if you write your programs with that discipline, then all you need to know is to know the name of the getter or setter or the function that you call from one language into another. And for that, we have an FFI-like encoding. It's literally just the Ethereum ABI encoding. Where you say this is the function name, these are the arguments, and I'm making the call. And once you make the call, then because each programming language has its own unique ID, right? So what will happen, the execution engine will identify first the ID of the programming language, and then it will execute that program with the semantics corresponding to that ID. But you see, the programming languages themselves are stored on-chain. There's nothing hidden.
And this was the crazy thing I saw. Is like you could just deploy a programming language, then all of a sudden people can use that programming language to then write programs.
You or anybody else. Once you deploy the language, it's a public good. So Ethereum Foundation should actually deploy the EVM semantics on-chain, because then nobody can argue what EVM is, right? Everybody will know that's EVM. But for us, all this is important because I don't know how else to verify things, right? We talk about verifiability. Verifiability is key in Web3. That's why we are in Web3, right? Because we want everything we do to be verifiable and everything others do to be verifiable. I don't want to be taken advantage of. For example, when Coinbase does a transaction for me, I have no idea if they sandwich me, if they, whatever that happened. I don't know. I would like to see a record of everything that happened, but I don't. Right? So that's why we like blockchains, because we can see everything. We can check everything. Everything is there, is verifiable. But now if you start thinking about going bigger, I don't want to depend on one particular programming language. I don't want to depend on a particular compiler and so on. I want verifiability. You become more and more demanding in what you want. Then you end up with mathematics, because there is no other way. You need a general convention for what computation is in order to be verifiable. I don't want to have, a verification engine for each programming language. That would be crazy, because then we have versions. Every 2-3 months, you have a new version of the language. Who can keep up with all of this?
More importantly, new bugs more frequently than sometimes every few months.
Exactly, bugs.
Yeah.
But if you have, a way to verify mathematics and then to reduce everything to mathematics, another nice thing is that when you can verify once and then use many times, right? So I can verify an execution once, like we discussed with a proof checker, a signed version of ZK, and now I can use that computational claim as many times as I want on different blockchains. If I want to implement a bridge, actually we implemented Wormhole using this approach. So then I can do a transaction on blockchain 1, and then I can verify it on the verifiable. We implement a verifiable settlement layer. We can also discuss about that at some point. But now this transaction happened on Ethereum, let's say, or on blockchain 1, becomes a claim that has been verified and settled on the verifiable settlement layer. And now I can take that to the destination chain and say, this is the proof that I've done this transaction on the source blockchain. So mint my tokens. Okay, so it's all automatic and and verifiable. You don't have to trust. The trust base is minimal.
I think, I can understand where not the pushback comes in, but kind of this gap where it's like, okay, you told me, and this is not the case, but like you imagine I have this huge stack of compilation down to machine code, and I don't know how any of that works. And then there's like a ZK part. I don't understand how that works. And now I'm just replacing that mental model with, now apparently this can turn into math and that math can now be checked. And I don't understand how that works either, but at least I get more out of it. So I think there's this interesting education problem to do around how to help people better intuit like what is actually going on here behind the scenes to make this into something that is, has these properties. So very interesting stuff. I used to work for Coinbase too, and I can say they didn't sandwich, at least at that time. So. But fair question. Yeah.
I'm a daily user of Coinbase.
There you
go. I'm happy that it exists. Let me put it this
way. So I guess now, someone's listened to this podcast now. We've been talking for about an hour, 80 minutes, hour and 20 minutes about K and how to use it and how it actually can be practically used in a blockchain environment.
Yes.
Now what? So I'm a developer. I'm like, this is sick. I've never been a fan of Solidity. I want to develop my own sort of semantics. And I think that this is going to be a much better way to develop programs. And now you're telling me I also get ZK provability or whatever you want to call your snark or stark verifying out of the box. What should I expect? So is this something you guys are going to release a virtual machine and get people to use it? Are you creating your own construction that people should expect to deploy to? How do you guys, where do you think things go from here? I think is maybe the question I want to ask.
Yes, I think the future is amazing once we incorporate and deploy this technology properly. And the way we want to do it is through what we call the verifiable settlement layer.
Okay.
Which you can think of it as a decentralized network of verifiers. So what's the idea here? The idea is that once you reduce everything to a common source of truth, you can have everything live together in one layer. So, like I mentioned, Wormhole, right? So what we do, we actually mirror different blockchains, L1s, L2s. We have partnerships with several companies like MegaETH, for example. So we mirror their block computations as claims on the VSL. VSL is the verifiable settlement layer that I'm referring to. So if a block happens, let's say on Ethereum, claiming that I go from state 1 to state 2 with this block, okay, we trust it because it's Ethereum and they have lots of validators and so on. But another way to do it is to simply verify that computation with the methods that I said before, with the mathematics and everything, and you now prove mathematically that yes, indeed, that code takes you from state 1 to state 2. Okay, and now I have a proof that that is indeed correct. Now, imagine to do the same thing with MegaETH, with Optimism, with Solana, with Bitcoin, right? With any Cardano, any blockchain out there. Now, what you have all these computational claims happening in all the layer 1s, layer 2s, even microchains in Linera. You have them all in one place and in one uniform notation and visible to each other because everybody can look at these facts. One way I like to explain it to my wife is that VSL is like Wikipedia with verifiable facts. Right? Imagine you have facts and then you have facts with a check mark. And that check mark means verified. We know it's true. So don't worry about its correctness anymore. So now if we have such checked facts, right, from all the blockchains, all the layer 1s and layer 2s, now we can rethink even how we develop applications, Web3 applications. I can have applications that are truly cross-chain, right? Because if I'm an AI agent, for example, and I want you to make me a payment before...
Got to get AI into this conversation. I love it. Yeah.
You can, but because for us, for VSL, there is no difference between blockchains and AI agents or Coinbase, for that matter. All of them for us would be claim generators. You generate a claim, you are in. Of course, we'll have to pay for the claim to be verified, but once verified, it's check marked, and now you can use it for whatever you want. Sky is the limit, your creativity. Right? So an AI agent can have you, for example, pay on Bitcoin for a certain service. Now that claim becomes immediately visible on the VSL, and now you know that thing is true. And now you can, as an agent, do the service that you paid for, right, for you, or an inference or a tuning or something.
So like basically by creating this, let's call it like a plane that has all these like truths about the world on it, in this case, really external or exogenous.
Yeah, we call it the verifiable settlement layer, VSL, for now.
It's a lot easier to write, or the claim will be to write applications that kind of interact with the world around it in a single place because it can, the whole world is unified into a single semantic framework, I guess. Yeah.
Exactly. And the claims themselves, they are very succinct. The proofs can be long, but once they are verified, they are discarded. You don't have to store them. And now you just know that these are facts which are true. And I can build on them.
Got it. So the what ends up happening is you have to find some way to stitch what becomes like a consensus mechanism from the outside world to understand what is final, I guess. But then once it's final, you can generate claims that then people can then interact over, I guess.
Exactly. Can you share again? Show you a picture. Maybe it's easier to discuss on a picture. Let me jump to here. Okay, so that's how we envision our VSL decentralized network or Pi-square decentralized network, right? It will be a decentralized network of validators, of verifiers. And the state, same like in a blockchain, right? The state will contain accounts with assets, code, storage, but also a set, and not a chain, a set of claims that are true, that have been checked and are settled as true. Okay, and the account holders are essentially users, applications with any programming languages and VMs, where it is established that, right? Different layer 1s, layer 2s, AI agents or service providers, provers, keys, anybody basically who can pay or be paid will have an account. And what the account holders do, they generate, if you see this arrow at the top here, they will generate claims. Okay, the claims are not settled yet. They need to be validated. Now, the validators will validate the claim. We'll have a decentralized network of validators that know only one thing to validate these claims. Okay, they validate a claim. Once you get a quorum, your claim is timestamped and settled, which means that it gets another proof, this little pi here. It's a very succinct proof. It's just a BLS signature. It's as efficient as that to be checked. The simplest possible cryptographic certificate that something, is true or something is claimed, right, an attestation. And now this is added to that Wikipedia of facts, right, checked facts. And anybody can use this C, including all these applications again here. Okay, so that's the flow. So you generate claims, they are verified and then settled when you get quorum. So it's the same like in a blockchain, but the difference is that there is no chain and no blocks. You can group maybe some of these claims because it's literally a set, not a chain, not a list, like a set data structure of facts. Same like in Wikipedia, the order of facts doesn't matter.
Sure.
They're just all there. Same here. And this enables a consensus protocol, which is unbelievably fast. I don't know if you are familiar with FastPay. FastPay is an amazing protocol. Strongly recommended to everybody who is interested in alternative payment systems. I believe that FastPay was invented in 2019. I think if it were invented before Bitcoin, we may not even have Bitcoin at this point. That's how much I like FastPay. I think it's a very powerful.
That came out of I think we talked about this previously too, but the Missin Labs group, or was that DM at that time that came out with the FastPay work? I forgot what it was. I'll link it in the show notes at the end.
Yeah. Right. Yeah.
That's my podcaster hat on.
Pod also was inspired by FastPay. FastPay inspired Pod, inspired also SUI, this single object protocol idea. So the idea is that if you have a single owner object protocol, the idea is that if there is only one owner that can change one object, then you can implement much faster consensus.
Yep.
And what we do here, we take that idea and expand it to maximum so that we don't lose any efficiency. Right? So we allow the same idea of FastPay, we extend it from payments only to actually claim settlement. Any claim that you make, it's settled, and it's the same algorithm that settles it that used for FastPay, which means that basically all you have to do is a round trip message from to a validator and back. That's it. That's how fast it's going to be. You don't have to wait for anybody anymore. Right? So imagine agents again. Suppose that you have 1 million agents operating at the same time for 1 million people around. Nobody has to wait for nobody else. An agent will be like its own blockchain. It will go from one state to another, to another, to another. All these computations will be verified because I want to trust that the agent does the right thing for me. Right? Yep. It is verifiable. Yet, no agent has to wait for any other agent. Now, if they do that on blockchains, they have to stay in line. And how many can do? Let's say maybe if everything works perfectly, like 5,000 maybe per second at this point with the existing blockchains, which is ridiculously low, right? We have to pass that stage. With this architecture that I'm showing here, there is actually no cap on throughput. You see, if I want more claims to be validated, because claims are completely independent of each other, like mathematical theorems, each mathematical theorem can be proved completely independently and in parallel with any other mathematical theorem. Same here, each claim can be validated independently and in parallel with all the other claims. If I want more throughput, I add more validators. I incentivize more validators to participate.
So basically what you end up getting bound by is like the number of conflicting assets or like storage slots that are being touched.
Yes.
I think is probably
basically causal dependencies. Yeah. Causal dependencies are unavoidable because I do the work for you once you pay me. So I have to wait for you to pay me and then I do the work.
Darn double spend problem. Yeah.
Right.
Yeah. But, okay.
Yeah. So that's the idea. Yeah. You can stop sharing now.
Yeah.
See each other. Yeah. But this is what we want to do, and we want to do this in about 6 months or so. We want to launch our testnet soon. But what this will enable I think will be amazing, because it's not only, that all these beautiful things that you go through, mathematical proofs, correct by construction and so on, but mathematics also unifies everything. Now we'll unlock the liquidity on all the blockchains that are integrated with the VSL. Actually, we internally joke, we don't call it TVL anymore, we call it TVU, which is total value unlocked.
Right? I never say total value of the universe or something like that.
Total value of the universe, yes, as well. But for us, for example, if we integrate with Cardano, let's say, now liquidity on Cardano is unlocked for applications that integrate with the Pi-square network. Same with Ethereum, Bitcoin, and so on. And moreover, actually, all these blockchains that are integrated also have access to everything else that happens in any other application that is integrated with the VSL, even if that is not a blockchain. If Coinbase decides to, let's say, dump their, every second or so, dump their state and prove their state, every second or so, now you can check that on Ethereum, and now you can do very interesting things, right? Like, do transactions conditioned by what happens on Coinbase in a decentralized exchange, and have, new arbitrage possibilities and so on and so forth.
New types of oracles, maybe. Yeah, interesting.
Right. So lots of things unlock once they are connected. So I think mathematics is the common ground for.
Yeah, I mean, I think it seems like a reasonable place to unify to is math, I guess. Everyone seems to be a big enough fan of that. Yeah, very cool. Well, I think this is probably a good place to start wrapping things up, because I think we've covered quite a stretch here. Thank you for the time, first of all, for coming on and explaining all this. I think I chalk this up to like the brave new world of what we can really do with programming languages. And it's been amazing to see, sometimes you have industries that push for different ideas because there's finally a need for that thing. And I think we started to see that with ZK stuff. And then now it's starting to become, into other areas that make, blockchains better. And then by proxy, hopefully the internet even better. And so this is, to me, is one of those things that has existed for a while and now is being forced, by you really to make it more practical for this world, and how it can be applied into different environments that it could really move the needle in terms of helping people feel more trust when they interact with these systems. So yeah, very, very cool to learn about. So yeah, thank you for taking the time. And yeah, if there's any final thoughts you'd like to share on, K, the journey here, how you guys are using that in Pi-square, the floor is yours.
Well, thank you so much for the questions. They're amazing questions, and it's such a refreshing pleasure to talk to an expert, technically expert also. So it was a great interview. I didn't even realize when 1 hour was passed. I would like to encourage your viewers to take a look at our network and become early developers. If we are going to launch our testnet by the end of the year, probably a devnet in a few months, but they should feel free to contact us right away. We can give them access to our devnet, and they can play with different languages and see what we're building.
Very cool. Yeah, it sounds awesome, and yeah, really excited to see the. Anytime we can make things safer in this industry, it's always a valiant effort. So applaud.
Especially if the mathematics goes under the hood, it just serves us.
Yeah. The thing that I still can't get my head around is like the leap to make it faster as a result of simplification you couldn't otherwise do is just
think so type cool. Checkers. Think type checkers, right? So type checkers are very complex mathematics. Maybe this is something nice to wrap up with, right? So type checkers are amazing mathematics, very complex mathematics. But first, you don't have to understand type checkers to use them in your programming language. You just get errors, fine. And then once you pass the type checking, which is like some proofs are done about your program, now your program will be faster than if you don't do type checking. Why? Because you can take advantage when you compile and execute the program internally of the fact that it's type safe. I don't have to check 3+ hello world because I know that will not happen. So that is the same principle, but pushed to extreme.
Yeah, just to a whole different level. Yeah, very cool. Yes. Awesome. Thanks for the time, and excited to see this stuff on a blockchain near you sometime soon. All right, appreciate it.